Welcome to G Fun Facts Online. In the Grand Cosmic Library, our solar system offers a surprisingly limited selection of books. We have small, rocky worlds and giant balls of gas. But out there, in the orbits of other stars, lies the most common type of planet in our galaxy, a type we don't have here at home, the super-Earth. These worlds, larger than our own, but smaller than Neptune, have shifted from science fiction to the front line in our search for extraterrestrial life. They are a planetary puzzle, and solving it might just help us answer the ultimate question: are we alone? The term super-Earth simply refers to a planet's mass and size, typically between 1 and 10 times the mass of our home world. What makes them so fascinating is their sheer prevalence, making up roughly a third of all exoplanets, and their complete absence from our own solar system. This fact alone challenges our models of how planets form. The first ones were found in 1992, but interest truly ignited in 2005 with the discovery of Gliese 876d, proving our galaxy is teeming with worlds that defy our local architecture. So how do you find a planet you can't see, dozens or even hundreds of light years away? It's a cosmic game of hide and seek, and astronomers have two main tricks. The first is the transit method. Imagine a moth flying in front of a distant streetlight. You can't see the moth, but you notice the light dim ever so slightly. That's what NASA's Kepler and TESS space telescopes do. They stare at hundreds of thousands of stars, waiting for that tiny periodic dip in brightness caused by a planet passing in front. The size of the dip tells us the size of the planet. Kepler was a game changer, revealing that super-Earths are a dominant population in the galaxy. Its successor, TESS, is now scanning the entire sky, finding nearby super-Earths that are perfect for a closer look. The second major technique is the radial velocity method, or the wobble method. A planet doesn't just orbit its star, its gravity also tugs on the star, causing the star to wobble in a tiny circle. We can't see the wobble directly, but we can see its effect on the starlight. As the star moves toward us, its light shifts to the blue end of the spectrum. As it moves away, it shifts to the red. By measuring this Doppler shift, astronomers can calculate the planet's minimum mass. This is how we confirm many of the worlds found by TESS and Kepler and get a crucial piece of the puzzle. Finding a super-Earth is one thing, but is it habitable? The first pass filter for astronomers is the habitable zone, also known as the Goldilocks zone. This is the orbital band around a star where temperatures are just right for liquid water to exist on a planet's surface. Not too hot, not too cold. The location of this zone depends entirely on the star. For a hot, bright star, it's far out. For a cool, dim red dwarf star, it's much smaller and snuggled up close. And this is where things get complicated, because a huge number of super-Earths have been found around these red dwarfs. Living close to a red dwarf is a double-edged sword. On one hand, these stars live for trillions of years, offering an incredibly long and stable time frame for life to evolve. But the close proximity means these planets are likely tidally locked, with one side in permanent daylight and the other in endless night. This could create scorching deserts on one side and a frozen wasteland on the other. Worse, young red dwarfs are temperamental, blasting their planets with intense X-ray flares that can strip away atmospheres and sterilize surfaces. However, a thick enough atmosphere could potentially redistribute heat, and the most stable place for life might be the Terminator zone, the twilight ring between day and night. But a planet's address isn't everything. For a super-Earth to be truly habitable, it needs more than just a good location. Its mass and gravity are a big plus. A more massive planet can hold onto its atmosphere much more effectively, which is essential for stable climates and protection from stellar radiation. A geologically active world is a living world. On Earth, plate tectonics regulates our climate over millions of years through the carbon cycle. The immense internal pressures on super-Earths could drive prolonged volcanic activity, which replenishes the atmosphere. This activity could also generate a powerful magnetic field. A magnetic field is a planet's invisible shield, deflecting the stellar wind that would otherwise erode its atmosphere. Excitingly, some models suggest super-Earths might have a second way to generate a magnetic field. A vast ocean of magma, left over from its formation, could churn for billions of years, creating a dynamo effect in the planet's mantle itself. The term super-Earth actually covers a whole menagerie of different planetary types. By combining a planet's size from transits and its mass from wobbles, we get its density, which tells us what it's made of. There are rocky super-Earths, which are essentially scaled-up versions of our own planet, potentially with continents and oceans. Then there are water worlds, completely covered by a single, global ocean that could be thousands of kilometers deep. While it sounds idyllic, this could be a problem for life, as a thick layer of high-pressure ice might form at the bottom, cutting the ocean off from life-sustaining minerals in the planet's rocky core. We also have theoretical eyeball planets, tidally locked worlds, where the only habitable zone might be a ring of perpetual twilight between the scorching day side and the frozen night side. At the larger end of the scale, we find mini-Neptunes. These worlds have a thick hydrogen and helium atmosphere, making them more like a small version of Neptune than a big version of Earth. There appears to be a size gap between rocky super-Earths and these gassy mini-Neptunes, suggesting a transitional point where a planet either holds onto its puffy atmosphere or has it stripped away. A particularly exciting new category is the Hycean world. That's a combination of hydrogen and ocean. These are large planets with globe-spanning liquid water oceans under a hydrogen-rich atmosphere. Their oceans could be similar to Earth's deep-sea hydrothermal vents, which host life that doesn't need sunlight. Let's meet some of these fascinating worlds. The closest exoplanet to us, just over 4 light-years away, is Proxima Centauri b. It's Earth-massed and in the habitable zone of its red dwarf star, but it gets blasted by intense flares, making its habitability doubtful. Then there's the famous TRAPPIST-1 system, 40 light-years away. It has 7 rocky planets, and at least 3 of them are in the habitable zone. TRAPPIST-1e is considered one of our best candidates for a habitable world, being very similar in size and mass to Earth. The James Webb Space Telescope is already studying its atmosphere, but the real headline grabber recently has been K2 to 18b, about 124 light-years away. It's a prime candidate for a Hycean world. JWST has detected carbon-based molecules in its atmosphere, and, most tantalizingly, a possible hint of a gas called dimethyl sulfide. On Earth, this gas is overwhelmingly produced by life, specifically marine plankton. This is not proof of life, but it's one of the most compelling clues we've ever found. So why haven't we confirmed life yet? Because this is incredibly hard. Trying to study the atmosphere of a planet light-years away is like trying to determine the ingredients of a cookie crumb from a mile away, while it's stuck to a searchlight. The signal from the planet's atmosphere is minuscule. A major problem is stellar contamination. Active stars, like red dwarfs, have dark spots and bright spots that can change over time. This stellar activity can perfectly mimic or completely hide the atmospheric signals we're looking for. A signal that looks like water vapor in a planet's atmosphere might just be a cool star spot on the star's surface. Our models for understanding these atmospheres are also still in their infancy. Different computer models can look at the exact same data from the James Webb Telescope and come up with very different conclusions about a planet's temperature and composition. This is why scientists are hunting for biosignatures, a smoking gun for life. On Earth, the biggest biosignature is our oxygen-rich atmosphere, created by photosynthesis. But even oxygen can have false positives. Intense UV light can break apart water molecules and create an oxygen atmosphere without any life. A more powerful approach is to look for disequilibrium, the presence of 2 gases that should exist together, like methane and oxygen. They react and destroy each other, so finding both in an atmosphere implies something is constantly producing them. On Earth, that something is life. For those Hycean worlds, Gases like dimethyl sulfide and methyl chloride are key targets, as they're almost exclusively produced by biology here at home. We are in a golden age of planetary exploration. The discovery of super-Earths has shown us that our solar system isn't the standard model. It might even be an outlier. These diverse worlds are the next great frontier. The James Webb Space Telescope is already giving us our first blurry glimpses into their atmospheres. And it's just the beginning. In the coming years, missions like Europe's Plato and Ariel and NASA's Nancy Grace Roman Space Telescope will build a vast catalog of new worlds. And looking to the 2040s, proposed observatories like the Habitable Worlds Observatory are being designed with one primary goal: to directly image an Earth-like planet and sniff its atmosphere for the telltale signs of life. The path is long and the challenges are immense, but with every new spectrum, every wobble of a distant star, we are piecing together a cosmic puzzle. Whether we find barren rocks, ocean worlds, or a living, breathing biosphere, the search for life on super-Earths is one of the most profound scientific adventures humanity has ever undertaken. The search is on,